All right, so last time we left off having talked about a little bit about the different patterns. We talked about some different kinds of sequences. In particular, we talked about arithmetic. And we talked about how to sort of identify the pattern, like a description with, variables in it for a pattern. We talked about geometric, same thing. And we encountered one sort of oddball sequence. Do you remember what it was? Fibonacci sequence as well. Sort of it kind of went across up. You're like, whoa, this is a little different, but it has a pattern too. We're going to talk about one more type of pattern today, and this pattern can be described visually. And it can be described visually with what are called figurate numbers. So these are numbers that are based on geometric patterns, providing examples of sequences that are neither arithmetic nor geometric. Such numbers can be represented by dots in the shape of the geometric figures. All right, so the first one we're going to talk about is triangular numbers, okay? So triangular numbers start with the number 1, and it looks like it's just a dot. Okay? And then the second one has 3 dots in the shape of a triangle. And the next one has 6 dots, and it's another triangle. Sometimes you kind of think this is a pyramid. I don't know, thinking cheerleaders, right? This is a cheerleader pyramid, but it's still a triangle. What do you think is going to happen as I move to the next one? With how many on bottom? 4 on bottom, and there will be 10 actually total. So I've got 4 on bottom, 3 on top of that, sort of offset, and then 2, and then 1. And then what am I going to do for the next one? 5 on the bottom. So it's kind of like we're building on the bottom and it sort of raises kind of it up or whatever. So I have 5 on the bottom, 4 on top of that, off-centered, 3 on there. That wasn't good on the last one. 2 on top, and then 1. And we can continue this pattern, right? These are called triangular numbers, and if you sort of identified how many dots are in each one of them, you would be able to create this sequence of numbers, 1, 3, 6, 10, 15, and so forth. So think with me, what would happen to the next one? How many more dots would it have? 6 more dots. Do you have to draw it to actually get that image? No, because we sort of established how the image works, right? So we could continue this pattern if we needed to, or if we were asked to. The next to the number in the pattern is actually going to be, so let me see this. This is plus 2. This is plus 3. We got this by doing 4 more, 5 more, and the next one would be what? Plus 6, giving me 21, and then I could do plus 7, giving me 28, and we can continue the pattern, right? All right, so these are figure numbers that are triangular numbers. The next one are square numbers. And you're going to see some other ones in your book when you get to here too, but the 2 I'm going to show you are triangular and square. All right, so square numbers again start out with the number 1. Then what shape do you think we might be making?
A square.
A square. And the first square we're going to do is going to look like sort of the 4 corners of a square. And it has how many dots? 4 dots. The next one I'm going to do is going to have 3 across and tall. And it had how many dots? 9. So it kind of looks like a square that would be like 3 units tall and 3 units wide, right? The next one would have 4 dots. And it would have how many dots? 16. Now, there isn't a real nice, well, I mean, it's not bad, but this formula, doing an addition of something, isn't quite as friendly as something else we could do. What would the next number be? 25. And then the next one? 36. Just for fun, Beth, go one more. 49. So how are we getting these numbers? We're squared. And that kind of makes sense, right? Because these are called square figure numbers. So as you're seeing this one, you're actually seeing that when, so for the nth term, let's say it this way, then you have m squared. is the number of dots. Right? I mean, and we could do what we did before. It would still work. Let me show you. Screen. This would get there by adding 3. How do we get from 4 to 9? We add 5. How do we get from 9 to 16? 7. How do you get from 16 to 9 to 25? Okay, so you can see that from that sort of a perspective too. I mean, it works. But it's really nice if you see the squaring pattern instead. Make sense? All right, so let me remind you of something we did last time just because it shows up really nicely in this problem. This idea of how much we add each time to get the next one, that's what we call a recursive formula. Remember, in order to do a recursive formula, you have to know where you're starting and where you're, and the pattern, how it ends up. This one down here was a general formula or a general term formula. And so we don't need to know what n equals, right? How many dots we had when n equal to 3. Because we can use any n value in that formula because it's a closed formula. It's not based on how many first numbers we had. Those are 2 different ways of describing numbers we did last time. All right, we're going to do one more. This is a real life situations we have, okay? All right, in fall of 2011, the newly formed Hurley College of Science and Mathematics had a meeting. On the board, the value 3.1415 was placed. And it had a dot, dot, dot at the end, indicating that there was more to be had after that. We were asked to find the next terms in the sequence of numbers. What would you say are the next terms? I want you to talk out loud. I want you to write down what you would suppose the next terms in the sequence of numbers are. I put this on the board and I said, what's the next? We'll do the next 3 terms. 2 terms, it says. The next 2 numbers in the sequence. Write down what you think the next 2 numbers are. No. Just write down the next 2 numbers. Okay, so somebody offer a suggestion to me. What did you write down? 1/6. Okay, and so 1/6 was the next 2, right?
Yeah.
Okay. Did anybody write anything else differently now? So I bring this up because I want you to think about how we think, because this is not what Haley wanted to write down. Otherwise, she wouldn't ask me about calculator. Haley, what did you want to write down? It looked like pi to you, didn't it? Okay. So if we were thinking that this number is pi, 9, 2 are the next 2 numbers. That would have been the next 2 numbers. So I mentioned this because it's an interesting idea, right? When we're looking at patterns, we're generalizing a specific case and moving into something that's not specific. Did we do inductive and deductive reasoning in this class? Right? This is one of those things. Right? This is inductive reasoning. It's taking a pattern and trying to create a general idea. Both of these are correct because you thought of it from a different pattern perspective. Okay? So, again, inductive reasoning means you've got room for error. And that's what it really means. It means you're generalizing something from a specific case example. Deductive reasoning, that doesn't happen to. So I wanted to bring it up because it was an interesting case of what happened.